So far, in our journey on graph theory, we saw how graph traversal works, how we can order events with precedence with topological sort, how to model a roadmap as a directed graph in order to find shortest path from one point to another point, and given a circuitry diagram model, how to find a wiring path which minimizes the required amount of wires with minimum span in trees. In this section, we are going to discuss about flow networks, which will allow us to model material flows like convey lines, water supply, or product transports, and finding maximum flow on such a network. In this diagram, I have modeled the flow network for XY hockey puck company's transportation problem for transporting hockey pucks from factory to its warehouse. XY company have its factory in Vancouver, which is the starting point for this transport, and in flow network we refer starting point of a flow as a source. And notice that from source vertex there are outgoing edges only, there's no incoming edges to source vertex. And XY company have its warehouse on Winnipeg, which in this case the endpoint for this transportation, and in flow network we refer such endpoints as sink. And also notice that we have only one source and one sink for any flow network. Now this transportation network has intermediate cities, and each edge in this flow network has capacity or maximum allowed trucks between any two cities. Now our target is to find maximum flow or the maximum allowed trucks to be transported between factory to warehouse. Now the problem here is that we cannot find the flow by simply adding these numbers. For example, if you consider the town Edmonton, we can transport 20 trucks of hockey pucks to Edmonton. But only 12 trucks of hockey pucks can only be transferred from the Edmonton. Since we are not storing any trucks in intermediate cities, it's obvious that actual incoming trucks for Edmonton will be less than the capacities of these edges. Therefore, we cannot simply add these numbers in order to find the maximum flow of the flow network. Okay, usually on top of edges, we are going to have number in this way. The right side number of this pair denote the capacity or the maximum allowed flow on that edge, such as 20 gallons of liquid or 20 amperes of current, and etc. The left side number is the flow or the current material moving rate. For given edge, flow is always less than the capacity, which is referred to as capacity constraint. Vertex in the flow network other than the source or sink denote the junction like cities in our previous example. Materials flows through these vertices without collecting on them. In other words, the rate at which material enters to the vertex must equal to the rate at which it leaves the particular vertex, and we call this property as flow conversion. For example, consider this diagram. There are three edges come to U vertex. So the total inflow of the U vertex is 7. So the total flow out from U vertex also should be 7, and it is 7 for this diagram. You can simply memorize this flow conversion property in this way. For any vertex other than source or sink, flow in should be equal to flow out. In a flow network, if there is an edge from vertex U to vertex V, then there cannot be an edge in other way around, which in this case from vertex V to vertex U. But however, if we come across such a scenario, we have to introduce intermediate vertex to graph as we did with the X vertex in the right side diagram. So to remove the reverse edge from vertex V to vertex U in the left side diagram, we have introduced the X vertex in the right side diagram, which has same capacity and same flow. In this way, we can convert anti-parallel edges to normal edges by using intermediate vertices. Now, I told you that we are considering single source, single sink flow networks. But actually, it's not quite accurate. We may come across flow networks with multiple sources and multiple sinks. In such cases, we have to convert such flow networks to single source, single sink flow networks by introducing super sources and super sinks. So here I have introduced super source and super sink to make multi-source multi-sink flow network to single source single sink flow network. Now notice that all the edges leaving the super source and all the edges come to super sink has infinity as capacity, hence adding these vertices will not be an effect to our flow network. Now these are some background facts that we need to know to continue to find a maximum flow of the flow network. So in the next video, we will see the short method of finding maximum flow of the flow network using max flow min cut theorem.